Hello there, and welcome to this quiet corner where the most violent events in the universe unfold with surprising gentleness. Tonight, we're not staying on Earth. We're venturing into the deep cosmos, where space and time themselves become players in a drama so vast and so energetic that it reshapes our understanding of reality itself. This is the story of what happens when two black holes collide, and it's a story that begins not with destruction, but with a dance that lasts billions of years. Picture this. Somewhere in the darkness, perhaps a billion light years from here, two objects exist that are so dense, so massive, that they bend the very fabric of space around them like bowling balls pressed into a stretched sheet. They have no surface you could stand on, no atmosphere you could breathe, no light you could see by. They are regions where space itself has been twisted so severely that nothing, not even light, can escape once it crosses their boundaries. They are black holes, and they are locked in an embrace that will define the final chapters of their cosmic story. But here's what's remarkable about this cosmic choreography. It doesn't begin with violence. It begins with patience. These two black holes might have been circling each other for longer than complex life has existed on Earth, spiraling inward with such gradual precision that if you could somehow watch from a safe distance, the changes would be imperceptible from one millennium to the next. This is deep time made manifest, a reminder that the universe operates on scales that dwarf human comprehension. The dance begins when these black holes are still separated by distances that would make our solar system seem cramped. They orbit each other in wide, stately loops, each one following the gravitational pull of its partner, while simultaneously creating ripples in the fabric of space-time itself. These ripples, predicted by Einstein over a century ago but only recently detected, are called gravitational waves, and they're carrying away energy from the system, energy stolen from the orbital motion of the black holes themselves. This is where the physics becomes almost poetic. As the black holes emit these gravitational waves, they lose energy, and as they lose energy, their orbits begin to decay. They fall closer together, not suddenly, but with the inevitability of water flowing downhill. The closer they get, the faster they orbit, and the faster they orbit, the stronger the gravitational waves become. It's a feedback loop written in the mathematics of general relativity, the equation that connects the motion of massive objects to the geometry of space and time. For billions of years, this process continues at a pace so leisurely that civilizations could rise and fall in the time it takes the black holes to complete a single inward step in their cosmic spiral. The gravitational waves they emit during this early phase are incredibly weak, carrying away energy at a rate so slow that the orbital decay is measured in fractions of millimeters per year. It's patient work, this reshaping of space and time, but it's relentless. But physics has a way of building toward crescendos, and this system is no exception. As the black holes draw closer, the rate of energy loss accelerates. What took millions of years in the beginning now takes thousands. What took thousands now takes decades. The mathematics that govern this process are elegant in their simplicity and terrifying in their implications. Each black hole, perhaps 30 or 50 or even 100 times more massive than our Sun, begins to feel the increasingly powerful tidal forces of its partner. This is where our story takes a turn from the merely astronomical to the genuinely exotic. When objects this massive get this close, the rules that govern ordinary matter begin to break down. The space between them is no longer empty in any meaningful sense. It's filled with gravitational fields so intense that they warp the very notion of straight lines. Light itself, if it somehow found its way into this region, would follow paths that curve and twist like ribbons in a hurricane. The black holes themselves begin to deform. Their event horizons, those boundaries beyond which nothing can escape, start to stretch and bulge under the influence of their partner's gravity. They're no longer perfect spheres, but elongated shapes that pulse and flex as they orbit. Each black hole is trying to pull matter from its companion, creating tidal bulges that race around the event horizons like waves on a cosmic ocean. And still they spiral inward. The orbital period, which might have been measured in days or hours, now counts down in minutes. The gravitational waves they emit are growing stronger, carrying away energy at an ever-increasing rate. But here's what's remarkable about this phase of the process. Despite the enormous forces involved, despite the fact that each black hole contains more mass than dozens of stars, the system remains surprisingly stable. The mathematics equations Einstein wrote of general relativity, those down in 1915, predict this behavior with stunning accuracy. As we watch this cosmic dance accelerate, we're witnessing something that pushes the boundaries of human understanding. The black holes are now moving at substantial fractions of the speed of light, their orbital velocities climbing toward values that would seem impossible for objects so massive. In the final minutes before merger, they might be circling each other hundreds of times per second, each orbit lasting mere milliseconds. The gravitational waves they emit during this phase are no longer subtle whispers in the fabric of space-time. They've become a crescendo, a tsunami of distorted geometry that propagates outward at the speed of light. If you could somehow stand in the path of these waves, equipped with instruments sensitive enough to detect them, you would witness space itself, stretching and compressing in a rhythm that matches the orbital dance of the black holes. The changes would be incredibly small, smaller than 1,000th of the width of a proton, but they would be there, measurable, real. This is the point where our story becomes not just about black holes, but about the nature of reality itself. Those gravitational waves carry information about the collision encoded in their amplitude and frequency. They tell us about the masses of the black holes, their spins, the shape of their orbits, even the orientation of the collision relative to Earth. It's as if the universe has developed its own form of communication, using the geometry of space-time to broadcast the details of the most energetic events it can produce. The waves that reach Earth millions or billions of years after the collision carry with them a kind of fossil record, a preserved memory of violence so extreme that it briefly outshines entire galaxies' worth of stars. But that violence is not chaotic. It's governed by laws, described by equations, predictable in its broad outlines, even if the details remain hidden in mathematical complexity that challenges our most sophisticated computers. What makes this story even more remarkable is that we're no longer just theoretical observers. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, achieved something that would have seemed like science fiction just decades earlier. It detected gravitational waves from a black hole collision, measuring those tiny distortions in space-time with precision that defies comprehension. Suddenly, we weren't just imagining these cosmic collisions. We were listening to them, hearing the universe speak in a language written in the mathematics of curved space-time. The detection revealed details about the collision that no telescope could ever observe. Two black holes, each roughly 30 times the mass of the Sun, had spiraled into each other 1.3 billion years ago. The gravitational waves from their final moments had been traveling through space ever since, carrying the news of their collision across the cosmos at the speed of light. When those waves finally reached Earth, they caused our planet to stretch and compress by amounts so small that they boggle the mind. But LIGO's first detection was just the beginning. Since then, dozens of black hole collisions have been observed, each one adding new details to our understanding of these cosmic events. We've seen collisions between black holes of vastly different masses, creating gravitational wave signatures that ring with harmonies and overtones like cosmic music. We've detected the spins of the black holes, measured their final masses, even observed how the collision products settle into their final stable configurations. Each detection brings us closer to understanding not just how black holes collide, but why they exist in the first place, how they form, and what their collisions tell us about the fundamental nature of gravity, space, and time. We're learning that these events are not rare cosmic accidents, but regular occurrences, happening somewhere in the observable universe, perhaps once every few minutes. The universe, it turns out, is full of black holes locked in these billion-year dances, each pair destined to eventual collision and merger. This ongoing story of detection and discovery has revealed that black hole collisions are among the most efficient energy conversion processes in the known universe. When two black holes merge, roughly 10% of their combined mass gets converted directly into gravitational wave energy, according to Einstein's famous equation, E=mc². That's a conversion efficiency that makes nuclear fusion look almost wasteful by comparison. The energy released in the final seconds of a black hole merger can exceed the combined light output of every star in the observable universe, though that energy is carried away by gravitational waves rather than light. As we continue to listen to these cosmic collisions, we're building a new kind of astronomy, one that relies not on light but on the direct detection of space-time distortions. It's changing how we think about the universe, revealing a cosmos that's far more dynamic and violent than we ever imagined, yet governed by laws so precise that we can predict the outcome of collisions between objects separated by millions of light years. The story of what happens when black holes collide is ultimately a story about the deepest nature of reality itself, about how matter and energy and space-time interact under the most extreme conditions the universe can produce. And as we'll see, the moment of collision itself is just the beginning of an even stranger tale. The final moments before collision unfold with a precision that would make a Swiss clockmaker weep. These two titans of space-time, each carrying the gravitational memory of dozens of dead stars, approach each other with orbital velocities that stretch our understanding of what it means for something to move quickly. They're no longer just black holes orbiting each other. They've become something new, something that exists in the space between physics and poetry. In these last seconds, the black holes are completing hundreds of orbits every heartbeat. Their event horizons, those invisible boundaries that mark the point of no return, begin to merge and separate, and merge again in a cosmic dance that defies visualization. The very concept of where one black hole ends and the other begins starts to lose meaning. Space itself has become so warped, so twisted, that the normal rules of geometry simply don't apply anymore. Here's where the story becomes almost impossible to tell in ordinary language. The gravitational fields are so intense that they create what physicists call a strong field regime, a place where Einstein's equations reveal behaviors that have no analogue in our everyday experience. Time itself becomes negotiable. What appears to last seconds from one perspective might unfold over entirely different durations from another. The black holes exist in a realm where causality itself gets stretched and twisted like taffy, but the universe has been patient with us, providing tools to understand even this extremity. The gravitational waves pouring out of this system carry information encoded in patterns that our instruments can decode. Each wave tells us something about the dance happening at the collision site. The frequency rises like a siren approaching, the amplitude growing stronger as the black holes accelerate toward their inevitable merger. It's as if the universe is narrating its own story, using the language of curved spacetime to describe events too extreme for words. The collision itself happens faster than thought. In the final milliseconds, the two event horizons touch and merge, creating a single, larger boundary around both black holes. But this isn't a gentle joining. The newly formed black hole is wildly unstable, its surface rippling and oscillating like a struck bell made of pure geometry. These oscillations send out their own gravitational waves, the final notes in a cosmic symphony that has been building for billions of years. What emerges from this violence is something that seems almost miraculous in its simplicity. After all the complexity of the merger, after all the warping and twisting of space-time, the final black hole settles into a form that can be described by just a few numbers. Its mass, its spin, its electric charge, if it has one. That's it. All the intricate details of the collision all the complex orbital dynamics that preceded it get erased. The black hole has no memory of how it formed, no scars from the violence that created it. This process of forgetting is built into the very nature of black holes. They're the universe's ultimate minimalists, storing enormous amounts of information in the simplest possible form. The event horizon that surrounds the merged black hole is perfectly smooth, perfectly symmetric, described by equations that are elegant in their mathematical simplicity. It's as if the universe has a built-in preference for clean outcomes, even from the messiest possible beginnings. But while the black hole itself forgets, the gravitational waves remember everything. They carry away not just energy, but information about every detail of the collision. The waves that spread outward at the speed of light are like a cosmic recording, preserving the story of the merger for anyone with the right instruments to detect them. In those wave patterns, encoded in frequency and amplitude and phase, lies the entire history of the collision. This is where the story becomes deeply personal for us as observers. Those waves travel for millions or billions of years, crossing vast reaches of empty space, carrying their message across cosmic distances that dwarf human comprehension. They pass through galaxies and stellar systems, through clouds of gas and dust, barely interacting with anything they encounter. They're almost ghostly in their passage, these ripples in space-time, detectable only by the most sensitive instruments ever constructed. When the waves finally reach Earth, they're incredibly weak. The collision that created them might have briefly outshone every star in the observable universe in terms of pure energy output. But by the time that energy reaches us in the form of gravitational waves, it spreads so thin across space that detecting it requires instruments capable of measuring changes smaller than the nucleus of an atom. It's like trying to detect the motion of a single grain of sand on a beach by listening to the ocean waves. Yet we can do it. The fact that we can detect these waves at all represents one of the most remarkable technological achievements in human history. The Laser Interferometer Gravitational Wave Observatory uses laser beams travelling through vacuum chambers 4 kilometers long to measure distortions in space, so small that they challenge our understanding of what measurement even means. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction, creating a pattern that can be extracted from the noise of 1,000 other vibrations. Each detection is like receiving a message from the deep past, a communication from the universe itself about events so extreme that they reshape our understanding of what's possible. The waves tell us not just that the collision happened, but when it happened, how massive the black holes were, how fast they were spinning, even the orientation of their orbital plane relative to Earth. It's forensic astronomy, using the evidence carried by gravitational waves to reconstruct cosmic crimes that occurred long before our solar system even existed. But here's what makes this story even more extraordinary. These detections have revealed that black hole collisions aren't rare cosmic accidents. They're happening all the time, everywhere in the universe. Our galaxy alone likely hosts millions of black hole pairs slowly spiraling toward merger. Some will collide next year, some in 1,000,000 years, some in 1,000,000,000. The universe is filled with these cosmic time bombs, each one counting down toward a collision that will briefly make it one of the most energetic objects in existence. The mathematics that govern these collisions are the same equations Einstein wrote down more than a century ago, when the idea of detecting gravitational waves was pure fantasy. Yet those equations predicted not just that the waves would exist, but exactly what they would look like, how they would propagate, what information they would carry. The fact that our detections match Einstein's predictions with such extraordinary precision is itself a kind of miracle, a reminder that the universe operates according to laws that we can discover and understand. We've learned that black holes can spin at tremendous rates, some rotating collisions between black holes so massive that they challenge at nearly the maximum speed allowed by relativity. We've seen our understanding of how such objects could have formed. we've detected mergers where one black hole vastly outweighs the other, creating gravitational wave signatures that ring with harmonies and overtones like cosmic music played on instruments made of pure space-time. Each new detection adds another piece to the puzzle of how black holes form, how they find partners, how they evolve over cosmic time. We're building a census of the black hole population in our local universe, mapping that lurk in the darkness between out the demographics of these invisible monsters are only beginning to understand. The story stars, some formed from the collapse of massive stars, others might have formed through more exotic processes. We of Black Hole Collisions is also teaching us about the nature of extreme physics, about what happens when matter and energy are compressed to densities that make atomic nuclei look sparse by comparison. These are natural laboratories for testing the fundamental laws of physics under conditions that could never be reproduced on Earth. Every collision is an experiment conducted by the universe itself, with results broadcast across space and time in the form of gravitational waves. As our detectors grow more sensitive and our network of observatories expands around the globe, we're entering an era where these cosmic collisions will become routine detections rather than extraordinary discoveries. We'll be able to study black hole mergers the way astronomers study stars, building up statistical samples that reveal patterns and trends in the black hole population. The universe will become our laboratory, and gravitational waves will be our primary tool for exploring it. But perhaps most remarkably, this is just the beginning. The black holes we've detected so far are the stellar mass variety, the remnants of dead stars. But there are also supermassive black holes, millions or billions of times heavier, lurking at the centers of galaxies. When those so powerful that they might be giants collide, they create gravitational waves detectable across the entire observable universe. Future detectors, some based in space where they can escape the vibrational noise of Earth, will listen for these galactic-scale collisions. They'll track the mergers of supermassive black holes as galaxies themselves collide and merge over cosmic time. We'll witness the formation of the largest structures in the universe, watching as the invisible architects of cosmic evolution reshape space itself through their gravitational dance. But there's something even more profound happening in these collisions, something that touches the very foundations of our understanding of reality. When black holes merge, they're not just combining mass and energy, they're testing the limits of what we know about the relationship between information and space-time itself. Each black hole that falls into the merger carries with it the quantum information of every particle that ever crossed its event horizon. Where does that information go when the black holes collide? This question sits at the intersection of quantum mechanics and general relativity, two theories that describe reality with stunning accuracy but seem fundamental to their extremes. Black-Pauli incompatible, when push-hole mergers are the universe's way of probing this incompatibility, creating conditions so extreme that they force us to confront the gaps in our understanding. The gravitational waves that emerge from these collisions might carry subtle signatures of quantum effects, whispers of physics beyond our current theories. Consider what happens to space-time itself during the final moments of collision. The fabric of reality becomes so distorted that the very notion of space and time as separate entities begins to break down. In those milliseconds of merger, the black holes exist in a realm where the familiar three dimensions of space and one dimension of time might not be sufficient to describe what's actually happening. Some theories suggest that additional dimensions, normally hidden from our perception, might reveal themselves in the extreme gravitational fields of merging black holes. The energy scales involved are almost incomprehensible. In the few milliseconds of the final merger, the power outputs in gravitational waves can exceed the combined luminosity of every star in the observable universe. That's not an exaggeration or a metaphor. For a brief moment, a single black hole collision outshines trillions of galaxies worth of stars. The fact that we can detect the whisper of this energy after it's travelled billions of light years and spread across the vastness of space speaks to both the incredible violence of the original event and the remarkable sensitivity of our instruments. But here's what's truly remarkable about this cosmic violence. It's creative. Every black hole merger creates something new, something that didn't exist before. The merged black hole has properties that are different from either of its progenitors. Its mass is less than the sum of the two original black holes because some of that mass has been converted to pure energy and carried away by gravitational waves. Its spin might be higher or lower depending on how the angular momenta of the original black holes combined. It's a kind of cosmic alchemy, transforming two objects into one through processes. The collision, also that operate at the very edge of physical law, creates something else entirely new. Those gravitational waves spreading outward at the speed of light are carrying energy and information that will eventually interact with matter throughout the universe. They're infinitesimally weak by the time they reach us, but they're still there, still stretching and compressing every black hole. Collision leaves its mark on the entire atom they encounter. In a very real sense, every light which can be absorbed, scattered or block universe, creating ripples that will propagate until the end of time. This brings us to one of the most beautiful aspects of gravitational wave astronomy. Unliked by intervening matter, gravitational waves pass through everything virtually unimpeded. They carry information about their source with perfect fidelity across cosmic distances and cosmic time. A gravitational wave detector on Earth receives essentially the same signal that would be detected anywhere else in the universe, modulated only by distance and the relative motion between source and observer. This means that gravitational waves give us an unobstructed view into the most violent and energetic processes in the universe. We can peer directly into the hearts of colliding black holes, witnessing events that unfold in regions of space where no light could ever escape. It's like having X-ray vision for the cosmos, allowing us to see through all the gas and dust and matter that normally obscures our view of distant objects. The precision of these measurements continues to astound even the scientists who make them. We can determine the masses of colliding black holes to within a few percent. We can measure their spins, track their orbital evolution, even determine how far away the collision occurred, all than 1,000th of the width of from detecting distortions in spacetime's smaller proton. It's metrology pushed to its absolute limits, measurement science operating at the boundary between the possible and the impossible. Each new detection also refines our understanding of how common these events actually are. Current estimates suggest that black hole mergers detectable by LIGO occur at a rate of roughly one every few days somewhere in the observable universe. That might not sound like much, but consider what it means. Right now, as you listen to these words, there are likely dozens of black hole pairs in their final moments before collision, their gravitational waves already travelling toward Earth but not yet arrived. The universe is constantly generating these cosmic catastrophes, a steady drumbeat of collisions that reshape space-time itself. The diversity of these collisions continues to surprise us. We've seen mergers between black holes of nearly equal mass, creating symmetric collisions that ring like perfectly tuned bells. We've observed highly asymmetric mergers where one black hole dramatically outweighs the other, producing gravitational wave signatures with complex harmonics that encode the details of the unequal partnership. Some black holes collide while spinning rapidly in the same direction, others while spinning in opposition, each configuration leaving its unique signature in the gravitational waves. Most intriguingly, we've begun to detect black holes that are so massive they challenge our understanding of stellar evolution. Stars can only grow so large before they become unstable, and the black holes they leave behind when they die should have masses that reflect this limitation. Yet gravitational wave detectors have found black holes that seem too heavy to have formed from single stellar collapse. This suggests alternative formation pathways, perhaps involving the merger of smaller black holes in dense stellar environments, or the direct collapse of primordial gas clouds in the early universe. These discoveries are forcing us to revise our models of how black holes form and evolve over cosmic time. The universe appears to be more creative in its black hole production than we previously imagined, finding ways to forge these objects under circumstances. Each a variety of conditions and new detection adds another data point to this emerging picture, helping us understand not just individual black holes, but the entire population of these objects across cosmic history. The future of gravitational wave astronomy promises even more extraordinary discoveries. Next-generation detectors will be sensitive enough to detect black hole mergers at the very edge of the observable universe, allowing us to probe the formation of the first black holes in cosmic history. We'll witness collisions that occurred when the universe was young, when the first generation of stars was dying and leaving behind these gravitational monuments to stellar death. Space-based gravitational wave observatories will open entirely new windows on the universe. Free from the vibrational noise of Earth, these detectors will be sensitive to lower frequency gravitational waves produced by the most massive black holes in existence. We'll watch as supermassive black holes at the centers of galaxies spiral toward collision over millions of years, tracking their orbital evolution in real time as galaxies merge and reshape the cosmic web. Perhaps most exciting of all, we're on the verge of detecting gravitational waves from the Big Bang itself, the ultimate black hole collision in reverse. These primordial gravitational waves, if they exist, would carry information about the first moments of cosmic existence encoded in distortions of space-time that have been propagating since the universe began. Finding them would be like discovering the universe's birth certificate, written in the language of curved geometry. But even as we push toward these future discoveries, it's worth pausing to appreciate the profound philosophical implications of what we've already learned. Black hole collisions represent the ultimate expression of Einstein's insight that mass and energy are equivalent, that matter and space-time are intimately connected, that the universe operates according to mathematical laws of stunning elegance and precision. Every gravitational wave detection is a reminder that we live in a universe far stranger and more wonderful than our ancestors could have imagined. We inhabit a cosmos where invisible objects dance for billions of years before colliding in explosions of pure geometry, where the fabric news of cosmic violence, across of reality itself, carries distances that challenge comprehension, where instruments built by curious primates on a small rocky planet can eavesdrop on the most energetic events since the Big Bang. The story of colliding black holes is ultimately a story about the power of human curiosity and ingenuity. These detections represent the culmination of centuries of theoretical work, decades of engineering development, and years of patient observation. They demonstrate that there is no limit to what we can discover when we combine mathematical insight with technological prowess and the simple desire to understand the universe we inhabit. As gravitational wave astronomy matures from a revolutionary discovery into a routine observational tool, we're entering an era where these cosmic collisions will become as familiar to astronomers as stellar spectra or galactic redshifts. But familiarity shouldn't breed contempt for the profound strangeness of what we're witnessing. Each detection represents a window into physics at its most extreme, geometry at its most distorted, energy at its most concentrated. The universe is teaching us that reality is far more flexible than time can we ever imagined, that space be stretch-eased and warped in, and sway ways that our everyday experience never prepared us for. Black hole collisions are laboratories, natural experiments in the malleability of existence for exploring this flexibility itself. They remind us that we live in a cosmos where the impossible becomes routine and the unthinkable becomes observable, where patient observation and careful measurement can reveal secrets hidden in the deepest structures of reality. And perhaps most remarkably, this story is far from over. We've only just begun to explore this new realm of gravitational wave astronomy, only started to decode the messages carried by ripples in space-time. Each new detector that comes online, each improvement in sensitivity, each refinement in our analysis techniques brings us closer to understanding not just how black holes collide, but what their collisions tell itself. The dance about the fundamental nature of existence continues, somewhere in the darkness, patient and relentless, and ultimately revelatory. And we, impossibly, are learning to hear its music. What's perhaps most haunting about these discoveries is how they've changed our relationship with emptiness itself. We used to think of empty space as truly empty, a void between objects, where nothing happened and nothing changed. But gravitational wave detections have revealed that this emptiness is alive, constantly trembling with the echoes of distant violence, carrying messages written in a language we're only beginning to learn to read. Consider what it means that right now, as you exist in this moment, gravitational waves from dozens of ancient collisions are passing through your body. They're stretching and compressing every atom urable, carrying information about events that occurred when the universe was younger, might as well be theoretical. Yet they're real, as you're made of by amounts so small, they and stranger than it is today. You are, quite literally, being continuously reshaped by dead billions of years before Earth even existed. This fixed stage upon which cosmic aftershocks of cosmic catastrophes that happen revelation has profound implications for how we understand the fabric drama unfolds. They have reality itself. Space and time aren't theational wave that passes represents a moment are the drama. Every gravit when the universe's most fundamental properties, its geometry, its very capacity to contain matter and energy, were altered by events of unimaginable violence. We're not just observers of the universe, we're participants in it, embedded in a medium that carries the memory of every massive object that has ever accelerated, every collision that has ever occurred. The mathematics that describe this phenomenon are beautiful in their inevitability. Einstein's field equations, written down in 1915, predicted with stunning precision what we would observe a century later. They told us exactly how massive distortions would propagate, objects would distort spacetime, exactly what signatures they would leave when they reached our instruments. It's as if the universe operates according to a hidden musical score, and Einstein glimpsed the notation, the music possible. But here's where system that makes the story becomes almost mystical in its implications. Those field equations don't just describe how matter tells spacetime to curve, they also to move. It describes how curved spacetime tells matter how's a conversation, a continuous dialogue between substance and geometry that plays out across cosmic scales. When black predetermined paths through space, they're actively reshaping the space hole's spiral toward collision. They're not just following through which they move, creating the very conditions that determine their ultimate fate. This feedback loop between matter and geometry reaches its most extreme expression in the final moments before merger. The black holes aren't just orbiting in spacetime anymore. They're orbiting in spacetime that they themselves are violently distorting with each passing moment. The gravitational waves they emit carry away energy, which changes their orbital characteristics, which changes the spacetime around them, which changes the gravitational waves they emit. It's a cascade of causation that builds toward an inevitable crescendo, each effect becoming the cause of the next effect in an accelerating spiral toward collision. The precision required to detect and analyze these events pushes the boundaries of what measurement means. We're using laser interferometry to track changes in distance that are smaller than the uncertainty principle would seem to allow. We're extracting signals from noise using statistical techniques that border on the miraculous. We're taking data corrupted by everything from earthquake tremors to traffic vibrations to the quantum fluctuations of light itself, and somehow finding within that chaos the whisper of events that occurred before our galaxy had fully formed. Each successful detection represents a triumph not just of technology, but of human stubbornness in the face of the impossible. The scientists who built these instruments spent decades developing techniques to measure the unmeasurable, to hear sounds that aren't sounds, to detect motion that doesn't involve the movement of any actual object. They created instruments so sensitive that they can detect the passage of a truck on a highway kilometers away, then somehow learn to distinguish thatching black holes. The data these instruments collect tells stories that read like science mundane vibration from the cosmic symphony of more we know. We can track the final fiction, but are grounded in the most rigorous physics death spiral of objects, so dense that a teaspoon of their material would outweigh a mountain. We can measure the spin rates of black holes that are rotating hundreds of times per second, their event horizons moving at substantial fractions of the speed of light. We can determine the masses of these objects with precision that would be impressive if we were weighing planets, but becomes almost incomprehensible when applied to objects whose gravitational fields are so their vicinity. The intense that time itself slows down in catalogue of detected mergers reads like a bestiary of cosmic monsters. There's GW114, the first detection, where two black holes, roughly 30 times the mass of the Sun, announced their collision with gravitational waves that had been travelling toward Earth for over 1 billion years. There's GW195, where black holes so massive they shouldn't exist according to our theories of stellar evolution somehow found each other in the darkness and merged to create something even more impossible. Each detection adds another entry to this growing census of the universe's most extreme objects. But perhaps the most remarkable aspect of this emerging field is how it's revealed the universe to be far more violent and dynamic than we ever suspected. These aren't rare exotic events. Hole mergers are occurring constantly, everywhere, are happening in distant corners of cosmic space. Black continuous background of gravitational violence that makes the universe ring like a struck bell. Every few minutes, somewhere in the observable cosmos, two black holes complete a haze that briefly outshines entire clusters of galaxies. This billion-year dance with a collision realization has forced us to confront the sheer scale of energy involved in these processes. When physicists calculated the energy output of that first detected merger, they found that in the final fraction of a second, the collision was producing gravitational wave power equivalent to 50 times the light output of every star in the observable universe combined. Not 50 times brighter than our Sun, 50 times brighter than every star we can see added together across the entire visible cosmos. The numbers are so large they lose meaning, becoming abstract representations of physical processes that operate beyond the scale of human comprehension. Yet somehow, impossibly, we can measure these events. We can extract from the tiny tremors they cause in space-time detailed information about what happened billions of years ago in regions of space so extreme that the normal rules of physics bend toward breaking. We can determine not just that a collision occurred, but when it occurred, how massive the participants were, how fast they were spinning, even the angle at which their orbital plane was oriented relative to our line of sight. This forensic capability has opened entirely new avenues for understanding the universe. We're using gravitational wave detections to measure the expansion rate of the cosmos, to probe the equation of state of matter at nuclear densities, to test whether Einstein's theory of general relativity holds up under the most extreme conditions nature can provide. Each merger becomes a natural experiment in fundamental physics, conducted under conditions that no laboratory could ever reproduce. The implications extend beyond physics into philosophy, forcing us to reconsider our place in the cosmic order. We are creatures who evolved on a small, stable planet, orbiting a well-behaved star, adapted to environments where the most extreme physics we encounter involves the occasional lightning strike. Yet through ingenuity and persistence, We've learned to eavesdrop on events so violent, they reshape the fabric of existence itself. We've become cosmic archaeologists, digging through the noise of terrestrial vibrations to uncover evidence of primordial violence written in the geometry of space-time. There's something almost mystical about the way history of the universe. The gravitational waves we detect today, these detections connect us to the deep, began their journey when the cosmos was younger, when different stars illuminated different skies, when the very matter that would eventually become our solar system was still scattered in interstellar clouds. These waves have been travelling for longer than complex life has existed on Earth, carrying their message across distances so vast that light from the collision hasn't even reached us yet. The future promises detections that will push these connections even deeper into cosmic history. Next-generation gravitational wave observatories will be sensitive enough to detect the mergers of the first black holes that formed in the universe, objects created when the very first generation of stars collapsed at the end of their brief, violent lives. We'll witness the deaths of stars that never knew planets, that burned in a cosmos without heavy elements, that lived and died in conditions so different from today's universe that they might as well have existed in an alien reality. Space-based detectors will extend our reach even further, allowing us to track the orbital evolution of supermassive black hole pairs over millions of years as they spiral toward collision at the centers of merging galaxies. We'll watch the universe's largest structures form in real time, witnessing the gravitational choreography that shapes the cosmic web itself. These observations will connect the smallest scales of physics to the largest scales of astronomy, revealing how quantum fluctuations in the early universe eventually grew into the galactic structures we see today. But perhaps the most profound discovery awaiting us lies not in the detection of more black hole mergers, but in what those detections will teach us about the nature of reality itself. Each gravitational wave carries information not just about the objects that created it, but about the medium through which it travels. By studying how these waves propagate across cosmic distances, we're probing the fundamental properties of space-time itself, testing whether the universe really does operate according to Einstein's equations or whether more exotic physics might be required. Some theories suggest that gravitational waves might carry signatures of extra dimensions, revealing aspects of reality that remain hidden from all other forms of observation. Others propose that the waves might show subtle deviations from Einstein's predictions, hints of new physics that only becomes apparent under the most extreme conditions. Each detection brings us closer to answering these questions, using the universe itself as our laboratory and gravitational waves as our experimental probe. The story of black hole collisions is ultimately a story about the power of patient observation and careful measurement to reveal truths about reality that seem almost too strange to believe. We live in a universe where invisible objects dance for billions of years before announcing their existence with explosions of pure geometry. We inhabit a cosmos where the fabric of space and time itself carries news of cosmic violence across distances that challenge comprehension. And we, somehow, have learned to listen to this cosmic conversation, to decode the messages written in the oscillations of space-time itself. Every gravitational wave detection is a reminder that the universe is far more remarkable than our everyday experience suggests. Reality operates on scales of half-human imagination, yet follows mathematical laws of time, distance, and energy that W such elegance and precision that conscious beings evolved on a small rocky planet can discover and understand them. We are part of a cosmos that seems designed for discovery, where curiosity and ingenuity can unlock secrets hidden in the deepest structures of existence. The dance continues, somewhere in the darkness, as it has for billions of years and will for billions more. Black holes spiral toward collision in a ballet choreographed by the fundamental forces of nature, their movements governed by equations that transform matter into geometry, and geometry into waves that carry stories across the cosmos. And we, impossibly, have learned to hear the music they make as they dance toward their inevitable, violent, creative embrace. What emerges from each of these cosmic collisions is something that challenges our most basic assumptions about permanence and information. When two black holes merge, they don't just combine their masses and spins in some simple arithmetic. They undergo what can only be described as a kin process, almost of cosmic amnesia. All information about their individual histories gets erased, leaving behind Anna's almost object that remember nothing about how it came to be. This forgetting isn't accidental. It's built into the fundamental nature of black holes themselves. The final merged black hole settles into a configuration that can be completely described by just three numbers: its mass, its spin, and its electric charge. Everything else, every detail about the complex orbital dance that preceded the merger, every characteristic that made the original black holes unique, simply disappears. It's as if the universe has a built-in preference for simplicity, even when that simplicity emerges from the most complex processes imaginable. But while Thegets, the gravitational waves, remember black hole for everything, they carry away not just energy, but a complete record of the collision, encoded in their frequency patterns and amplitudes. These waves are like cosmic historians, preserving details about the merger that the merged black hole itself has already discarded. The information doesn't disappear, it just changes form, transforming from the properties of massive objects into the oscillations of spacetime itself. This transformation reveals something profound about the relationship between information and energy in our universe. When mass converts to gravitational wave energy during the merger, it's not just matter changing into radiation. It's information changing its storage medium, moving from being encoded in the structure of massive objects to being written into the geometry of space and time. The waves that spread outward at light speed carry with them a kind of cosmic memory, a record of violence that will persist until the end of time. The precision of this information encoding is remarkable. Hidden within the gravitational wave signal are details about the collision that would seem impossible to extract. Scientists can determine not just the masses of the original black holes, but how those masses were distributed, how fast each black hole was spinning, even the orientation of their spins relative to their orbital motion. It's forensic astronomy at its most sophisticated, using the faintest tremors in spacetime to reconstruct events that occurred under conditions no laboratory could ever replicate. Each parameter leaves its own signature in the gravitational waves. The total mass determines the overall frequency of the signal. The mass ratio affects how the frequency changes over time. The spins influence subtle modulations in the wave amplitude. Even the angle at which we observe the collision relative to the orbital plane shows up as characteristic patterns in the data. The waves are like musical compositions, where every note carries meaning. Every harmony encodes information about the cosmic instruments that created them. More remarkable is that it happens despite the incredible sound. What makes this information extraction even weakness of the signals by the time they reach Earth? A gravitational wave that began as the product of cosmic violence, equivalent to the total light output of the observable universe, arrives at our detectors as a disturbance so faint it barely registers above the quantum noise limit of our instruments. Yet from this whisper, we can reconstruct the roar of the original collision with stunning accuracy. The mathematical techniques required to extract this information push the boundaries of what computation can achieve. Scientists use sophisticated algorithms that compare the detected signals to millions of theoretical waveforms, searching for the best match between observation and prediction. It's like having a vast library of cosmic sheet music and trying to identify which piece is being played based on hearing just a few faint notes through enormous amounts of noise. These computational challenges have driven innovations in data analysis that extend far beyond gravitational wave astronomy. The techniques developed to find black hole mergers in noisy data are now being applied to everything, from medical imaging to financial modelling. The universe, in teaching us to hear its most subtle voices, has also taught us new ways to find signals hidden within complexity. The catalogue of detected mergers continues to grow, with each new detection adding another piece to our understanding of how black holes behave under extreme conditions. We've observed mergers where the black holes had nearly identical masses, creating symmetric collisions that produce clean, easily analysed signals. We've also detected highly asymmetric mergers where one black hole dramatically outweighs its partner, producing gravitational waves with complex harmonics that encode the details of the unequal partnership. Some of the most intriguing detections involve black holes spinning at tremendous rates, rotating at substantial fractions of the maximum speed allowed by relativity. These rapidly spinning black holes create gravitational waves with signatures that are challenging to model and analyse, pushing our theoretical understanding to its limits. The extreme spin rates suggest formation mechanisms that go beyond simple stellar collapse, hinting at more exotic processes in the early universe or in dense stellar environments. And so we arrive at the end of our journey through the cosmos, though the dance itself continues unabated in the darkness. What we've witnessed together is nothing less than the universe teaching us its most profound lessons about the nature of reality, written in the language of curved space-time and delivered through ripples that travel for billions of years, just to whisper their secrets into our instruments. These collisions remind us that we live in a cosmos far stranger and more beautiful than we ever dared imagine, where the impossible becomes routine and the unthinkable becomes measurable. As you drift off to sleep tonight, remember that you are part of this cosmic story, continuously reshaped by echoes of ancient violence, connected to the deepest structures of existence through forces you cannot see, but which shape every moment of your being. Every moment of your being.